26 light-years from Earth, astronomers have spotted something that seemingly shouldn't exist. A planet so close to its star that its surface can melt metal, yet signs of water vapor appear in its light. The discovery has scientists around the world stunned. This rocky planet, named GJ486b, orbits its star so closely that a single year there lasts just 36 hours. Surface temperatures soar to 800 degrees, hot enough to destroy any atmosphere instantly. And yet, the James Webb Space Telescope detected the telltale signature of water in the infrared light filtering through this alien world. But here's where things get strange. That water may not actually belong to the planet at all. It could be a mirage, hidden in the cool, dark spots of the star itself. If that's true, it would overturn what appeared to be the first ever discovery of an atmosphere on a rocky planet beyond our solar system. The signal first appeared on the monitors at the Space Telescope Science Institute, faint and mysterious, like a whisper from another world. Scientists had aimed humanity's most powerful observatory at GJ486b, expecting to see nothing. Instead, they found water vapor, something that shouldn't exist on such a scorched world. This wasn't a gas giant like Jupiter, where water is common. This was a super-Earth, rocky and dense. If the readings are correct, it would mark the first confirmed atmosphere around a rocky exoplanet, a monumental breakthrough. The telescope observed GJ486b as it passed in front of its star twice, each transit lasting about an hour. During those moments, starlight filtered through what should have been its upper atmosphere. That light carried chemical fingerprints, revealing the unmistakable signature of water molecules, absorbing specific wavelengths of infrared. Light, 3 independent research teams analyzed the data using different methods, and all reached the same conclusion: water vapor. Yet a new mystery emerged. Red dwarf stars, the kind this planet orbits, often have star spots, cooler regions much like sunspots on our own sun. These regions are cold enough for water vapor to exist on the star's surface itself, not the planet's. Computer simulations compared both possibilities, a planet with a watery atmosphere versus star spots containing water. The results? Nearly identical. As Sarah Moran from the University of Arizona explained, we see a signal that almost certainly comes from water, but we can't yet tell whether that water belongs to the planet or the star. The uncertainty has scientists both frustrated and fascinated. For decades, astronomers have searched for atmospheres around rocky exoplanets. They've found them around gas giants and hot Jupiters, but never on a small, rocky world resembling Earth. Even if this one feels more like hell than home. If this planet truly has an atmosphere, it could rewrite what we know about rocky worlds, proving they can hold on to air even under extreme radiation and heat. And if such a scorched planet can manage that, then imagine the billions of cooler, calmer planets across the galaxy that might do the same. But first, we must understand the planet itself. Picture Earth, but compressed until it's 3 times heavier and only 30% larger. That's GJ486b, a world where gravity would crush you, tripling your weight with every step. Astronomers classify it as a super-Earth, rocky like our planet, but smaller than Neptune or Uranus. It was first discovered in 2021, when scientists noticed a slight dimming in its star's light as the planet passed by. Located in the constellation Virgo, visible in Earth's northern skies during spring, this planet is anything but serene. Its surface burns at 800 degrees Earth, hot enough to melt lead, zinc, and even soften rock. The planet's density shows it's made of iron and stone, much like Earth, but that's where the similarities end. Using the dimming of starlight, astronomers determined its size. Measuring the subtle wobble of the star revealed its mass. Combine the two and you get density, the key to knowing what it's made of. Dense planets like GJ486b are built of tightly packed metals and eat minerals, but whether that density hides an atmosphere rich in water, vapor, or merely reflects a cosmic illusion from its star, remains one of astronomy's most thrilling mysteries. Gas giants are lightweights in comparison. Their low densities come from hydrogen and helium spread thin across massive volumes. But GJ486b is the complete opposite. Its density screams rock and metal, a world forged in fire and pressure. This planet completes a full orbit in just 1.5 Earth days. Think about that. A year here is shorter than a weekend on Earth. GJ486b races around its star at blistering speed, locked so close that it nearly kisses the star's surface. That closeness is both a curse and a gift. The curse? The planet is constantly bombarded by deadly radiation, its surface roasted by its fiery neighbor. The gift? Its proximity makes it easier to study. Every time it crosses in front of its star, it blocks a significant portion of the starlight, creating a strong, clear signal for telescopes like James Webb to analyze. But there's something even more fascinating about this world. Something that twists the very idea of what day and night mean. Unlike Earth, GJ486b doesn't spin freely. It's tidally locked, meaning one side of the planet always faces its star, trapped in endless daylight and searing heat. The other side is plunged into eternal darkness, frozen and still. Between these extremes lies a razor-thin border called the terminator, where day meets night, a chaotic twilight zone. If the planet truly has an atmosphere, that narrow region could roar with supersonic winds, carrying heat from the burning day side to the icy night. But if no air exists, then one side burns while the other freezes solid. Everything depends on that single, unanswered question. Does this world have an atmosphere at all? Now, let's talk distance. 26 light years. It sounds far, until you realize what it means. A single light year equals about 6 trillion miles. The distance light travels in 1 year at 186,000 miles per second. Multiply that by 26, and you have the distance between Earth and GJ486b. But in cosmic terms, that's practically next door. The Milky Way galaxy stretches about 100,000 light years across. GJ486b sits within a tiny fraction of that span, practically in our local neighborhood. To visualize it, imagine the Milky Way as the entire United States. Earth would be somewhere around Kansas City, while GJ486b would be just 2 blocks away. Meanwhile, the Andromeda Galaxy, our nearest major galactic neighbor, would lie in an entirely different country. The scale of the universe is staggering, and yet this strange planet lives right beside us. The star it orbits, GJ486, is a red dwarf, also known as an M-dwarf star. These small, dim stars make up nearly 70% of all stars in the universe. They're cooler and fainter than our Sun, yet far more numerous. GJ486 has about 30% of the Sun's mass and shines with just 2% of its brightness. From Earth's distance, you could look straight at it without harming your eyes, though you'd need a telescope to see it at all. In our sky, it appears as a faint red pinprick, invisible without the aid of modern optics. Because red dwarfs are so dim, any planet seeking warmth must orbit extremely close to its star, deep within the zone where liquid water could exist. This region is known as the habitable zone. But GJ486b orbits even closer than that, well inside the safe zone, which is why its surface burns at metal melting temperatures. Yet this closeness provides scientists with an invaluable advantage. The stronger the starlight signal, the easier it is to detect atmospheric gases. When studying such faint worlds, every factor matters. Distance. Closer planets are easier to analyze. Brightness. Dimmer stars make subtle signals clearer. Planet size. Larger planets block more light during transits. And GJ486b checks all those boxes. It's nearby, large enough to produce a measurable dip in light, and passes in front of its star regularly, offering multiple chances for observation. But there's a dark side to that convenience. Being so close to a red dwarf means living under constant threat. These stars may seem weak and cool, but they're cosmic tempests, monsters disguised as embers. Red dwarfs unleash violent solar flares, bursts of X-ray and ultraviolet radiation that can multiply their brightness by 10 to 100 times within minutes. Imagine our sun suddenly shining 100 times brighter. Earth's atmosphere would be stripped away, oceans would boil, and life would cease in moments. That's daily life for planets like GJ486b. The danger is even worse when red dwarfs are young. For their first billion years, they throw relentless tantrums. Storms of energy that tear at nearby planets day after day, century after century. Any atmosphere that forms is slowly ripped apart. Ultraviolet light splits water into hydrogen and oxygen. The light hydrogen escapes into space, while the heavier oxygen reacts with the surface or disappears into the void. Eventually, the planet is left bare and airless. GJ486 itself is billions of years old, long past its most violent youth. But the damage from those early eons may have already been done. Astronomers believe the star spent ages, bombarding its planets with lethal radiation, enough to strip away any atmosphere that ever existed. That's why the presence of water vapor detected by James Webb is so astonishing. This planet should be dead and dry, a lifeless rock circling a dying ember. Yet somehow, water's fingerprint still appears in its light, and that mystery grows even deeper when you realize one last thing about red dwarfs. They barely age. While our sun will live around 10 billion years in total, red dwarfs can burn for trillions. They are, in essence, immortal fires. Slow-burning stars that could outlive the universe as we know it. Red dwarfs are the eternal fires of the cosmos. These tiny stars can burn for up to 10 trillion years. That's 1,000 times longer than our sun's lifespan. For perspective, the entire universe is only about 14 billion years old, which means not a single red dwarf has ever died of old age. Every one of them is still in its youth or middle age, and they'll continue to glow long after stars like our sun have faded into cold white dwarfs. This incredible longevity opens a profound possibility. If rocky planets orbiting red dwarfs can somehow hold onto or rebuild their atmospheres despite constant radiation, they would have trillions of years for life to emerge and evolve. Trillions of years for civilizations to rise and fall, countless times over. That's why scientists are so fascinated by JJ 486b. It's not just about this single planet, it's about what it represents, the billions of rocky worlds orbiting red dwarfs across the galaxy. If one of them can sustain an atmosphere, the door to eternal habitability opens wide. But before answering that cosmic question, we need to grasp just how strange JJ 486b's orbit truly is. A year on this planet lasts just 36 hours, shorter than 2 nights of sleep on Earth. While we're dreaming through a weekend, JJ 486b completes an entire orbit around its star. It hurtles through space at a breathtaking 200,000 miles per hour, tethered only by gravity's invisible grip. At that speed, you could travel from New York to Los Angeles in 80 seconds. The planet's orbit is incredibly tight, only 2 million miles from its star, about 1/50th the distance between Earth and the Sun. Such proximity leads to bizarre consequences. There are no seasons on this world, no gentle transitions from summer to winter, no months, no years in any familiar sense. If humans could somehow exist there, which they absolutely could not, they would celebrate a birthday every day and a half. A teenager would technically be thousands of years old in Earth terms. Time itself would lose meaning. From the dayside surface, the red dwarf would dominate the sky, appearing 15 times larger than our sun does from Earth. It wouldn't shine as bright white-yellow light, but rather a deep, glowing crimson, flooding the landscape in fiery orange-red hues. Standing under it would feel like being beneath a massive, burning ceiling pressing down from above. The light would be dimmer, but the sheer size of the star would be overwhelming. A silent, smoldering presence hanging eternally overhead. Scientists had been able to map JJ 486b's motion with astonishing precision. Every time the planet crosses in front of its star, a moment known as a transit, the star's brightness dips ever so slightly. Those dips occur with clockwork regularity, every 1.467 days. This consistency tells us the planet's orbit is stable. It's neither spiraling into the star nor drifting away. Instead, JJ 486b is locked in a perfect gravitational dance, likely unchanged for billions of years. But here's where things get truly unsettling. The planet itself doesn't experience that 36-hour cycle. Though it races around its star every day and a half, it doesn't spin. JJ 486b is almost certainly tidally locked, meaning one side always faces the star, while the other side is trapped in eternal darkness. This phenomenon completely transforms what it means to be a world. Imagine standing on the dayside, the sun never moves. It hangs frozen in the same spot in the sky, never rising, never setting, just blazing endlessly. The surface beneath you scorches under permanent daylight. Now imagine walking to the planet's far side. There, the sun never appears. The landscape is pitch black, frozen solid, an eternal night untouched by warmth or light. Between these two extremes lies a thin ring of twilight, the Terminator Zone, where the star forever hovers on the horizon, casting an endless sunset across a world locked in stasis. This strange balance exists because gravity from the star pulls harder on the planet's near side than the far side. Over millions of years, this differential tug acts like a brake, gradually slowing the planet's rotation until it becomes perfectly synchronized. One face eternally burning, the other forever frozen, a world caught between fire and ice, turning never again. The planet gradually slows its rotation, little by little, until one day, it simply stops spinning altogether relative to its star. From that moment on, one side forever faces inward toward the blazing red sun, while the other side remains in perpetual darkness. It's the same phenomenon that keeps Earth's moon tidally locked to us. We always see the same lunar face. GJ 486b is almost certainly locked in this same cosmic embrace. The result? A dayside that scorches at around 800 degrees 426 degrees, while the night side may plummet to hundreds of degrees below freezing, possibly nearing absolute zero, depending on whether an atmosphere exists to carry heat around the planet. Without air, the night hemisphere would be an unending frozen desert where even gases like carbon dioxide would solidify into ice. The terminator zone, that razor-thin boundary between never-ending day and endless night, could be the only region with survivable temperatures. Not pleasant, not mild, just barely tolerable. There, the red dwarf would hang eternally on the horizon, locked in a state of permanent sunrise or sunset. But this is where the mystery deepens and ties directly into the question of water vapor. If GJ 486b does have an atmosphere, everything changes. Air moves, pressure shifts. The superheated day side would produce rising air and lower surface pressure, while the icy night side would have sinking air and higher pressure. This contrast would unleash winds screaming at supersonic speeds, racing from night to day, redistributing heat across the planet and softening the extremes. Scientists can test this theory by examining the planet's temperature map. If the hottest point lies directly beneath the star, it suggests still air, little to no atmosphere. But if that heat peak is shifted eastward, downwind from the substellar point, that would indicate strong winds and, therefore, an atmosphere. Future telescope observations may reveal the truth. For now, all astronomers have is that faint, stubborn signal of water vapor, mysterious and frustratingly unclear. But the temperatures themselves tell a chilling truth. 100 degrees south. Let that number settle for a moment. At 450 deg, paper bursts into flame. At 621 degrees, lead liquefies. At 786 degrees, zinc melts. GJ 486b exceeds them all. If you somehow stood on its surface, which you absolutely could not, your body would ignite instantly. The rocky ground beneath your feet would glow faintly red from its own heat, and any water would vaporize the instant it touched the surface. Scientists determined these temperatures through multiple approaches, measuring the star's light output, calculating how much radiation the planet absorbs, and estimating its reflectivity. Every method converged on the same result: a world existing at the edge of what solid rock can endure. For comparison, basalt, one of Earth's most common volcanic rocks, softens near 2000 degrees, 1093 degrees. GJ 486b isn't quite that hot, but it's within a regime where minerals behave strangely, some rigid, others pliable like warm wax. Consider Venus, the hottest planet in our solar system, with a surface temperature near 870 degrees, 465 degrees. But Venus's inferno is sustained by a thick, crushing atmosphere of carbon dioxide, 90 times denser than Earth's air. The greenhouse effect is so extreme that Venus's night side is nearly as hot as its day side. GJ 486b might not have that luxury. If it's airless, the temperature difference could be staggering. 800 degrees on the day side, possibly 300 degrees on the night side. A swing of more than 1000 degrees across the twilight boundary. That poses a question. If water vapor truly exists here, where could it come from? The surface is far too hot for liquid water, and any ancient supply would have boiled away eons ago. The only plausible source is volcanic activity, steam venting from the planet's molten interior. Beneath its crust, immense pressure could keep water trapped as superheated liquid or vapor. Volcanic eruptions might then release bursts of steam into the thin atmosphere, temporarily replenishing it. But there's a catch. For this to be true, GJ 486b must still be geologically alive, its interior hot enough to sustain volcanic eruptions and tectonic motion. With a mass 3 times that of Earth, it's possible the planet retains heat deep inside. But scientists don't yet know for sure, and that leads us back to the heart of the mystery. Is the water vapor coming from the planet or from the star itself? Red dwarf stars, like the one JJ486b orbits, are known for star spots, dark, cooler regions caused by magnetic activity, similar to sunspots on our sun. But these are far colder. While sunspots drop from about 10,000 degree F to 7,000 degree F, red dwarf star spots can plunge from 6,000 degree F to 4,000 degree F, cool enough for water vapor to exist. Our sun is simply too hot for that. But a red dwarf's cooler spots might naturally harbor traces of water vapor. That's the confounding puzzle. Is the signal of water a clue to alien volcanism, or just an illusion painted on the surface of a restless, burning star? Scientists confirm this mystery through a powerful technique called spectroscopy, a method that reads the chemical fingerprints hidden in light. They discovered that water vapor does exist in the atmospheres of cool stars, collecting in their dark, cooler star spots. But that discovery leads to a serious complication. When a planet passes in front of such a star, what astronomers call a transit, it might cross directly over one of these star spots. During that brief alignment, the light filtering through the planet's possible atmosphere also picks up the signature of the star spot's water vapor. The result? The two signals merge, blending together so completely that distinguishing one from the other becomes nearly impossible with current technology. To tackle this problem, researchers built detailed computer models to simulate both possibilities. In one scenario, the water came from the planet's atmosphere. In the other, it originated from the star's spots. Both models, surprisingly, matched the James Webb Space Telescope's real observations almost perfectly. The difference only appears at shorter wavelengths of light, below the range that Webb's NIR-SPEC instrument can observe. That's why astronomers are now waiting for follow-up observations, with another instrument called NIRISS, which can see those shorter wavelengths. If the water signal grows stronger at those wavelengths, it likely comes from the star's surface. If it weakens or disappears, it's probably from the planet's atmosphere instead. Until those new observations arrive, the mystery remains open. The challenge doesn't stop there. Red dwarf stars like GJ486 are incredibly magnetically active, often covered in star spots, sometimes across 10% or more of their surface. When a planet the size of GJ486b crosses such a star, it's almost certain to pass in front of at least one star spot during its hour-long transit. That contamination is unavoidable. Every time scientists study a red dwarf planet, they face this same uncertainty. Astronomers first warned about this problem years ago. In 2018, researchers at the University of Arizona predicted that star spots on red dwarfs could perfectly mimic the signs of an atmosphere. They cautioned that separating the two would become one of the biggest challenges in exoplanet science. And now, with GJ486b, that prediction has come true. The very first attempt to detect an atmosphere on a rocky, world-orbiting a red dwarf has run straight into this puzzle. But the James Webb Telescope is uniquely equipped to cut through the confusion, because light tells stories. Every time light passes through gas, specific wavelengths get absorbed, while others pass through untouched. This pattern of missing light forms a unique molecular fingerprint. For example, water vapor absorbs strongly at certain infrared wavelengths. Carbon dioxide absorbs at others. Methane has its own distinctive signature. By spreading starlight into a rainbow-like spectrum and carefully measuring which colors are missing, scientists can determine the chemical makeup of a planet's atmosphere, all without ever leaving Earth. This process is called transmission spectroscopy, and it's transforming how we understand distant worlds. Here's how it works for GJ486b. The planet completes one orbit every 36 hours. Once each orbit, it passes directly between its star and Earth. During that 1-hour transit, a small portion of the star's light filters through the planet's thin outer layer, its atmosphere, if it has one. If the planet has no atmosphere, the light simply glances off its rocky surface and continues. But if there's air, the light interacts with the gas, and molecules in that air absorb specific wavelengths. Water vapor, for instance, vibrates and rotates in response to infrared light, taking away precise portions of the spectrum and leaving tiny dips that reveal its presence. The Webb Telescope's NIR-SPEC instrument which observes infrared wavelengths between 0.6 and 5.3 microns, captured two separate transits of GJ486b. In both, the same water absorption pattern appeared. That consistency meant the signal was real, not a random glitch or instrument error. Each observation lasted about an hour, enough time for Webb to gather thousands of photons and build a detailed spectrum. Most of the data looked flat, showing the planet blocked about the same amount of light across most wavelengths. But at the shortest wavelengths, around 1 micron, Webb detected a distinct rise, a small bump in the data. That bump aligned perfectly with the fingerprint of water vapor. Whether that vapor belongs to the planet's atmosphere or the star's spots, however, is a question that remains tantalizingly out of reach. For now. The results weren't crystal clear. The error margins, the uncertainty range in the measurements, overlapped between the atmospheric and starspot models. Yet the signal persisted, tantalizing, frustratingly ambiguous. 3 independent research teams analyzed the same data using different statistical techniques, and all 3 arrived at the same result. The bump most likely indicated water vapor, but they also agreed that starspots could just as easily explain it. The data simply wasn't clean enough to tell them apart. That's the constant challenge of working at the edge of technological limits. You uncover hints, suggestions, possibilities, but not definitive answers. The fact that scientists observed the planet twice reveals something vital about their process. Observing once gives you a clue. Observing twice gives you science. When the telescope first caught GJ486b passing in front of its star, researchers immediately noticed the telltale water vapor signal. They knew they needed confirmation. Time on space telescopes is precious, each hour fiercely contested by hundreds of global teams. But the potential discovery of an atmosphere on a rocky exoplanet was worth a second look. Approval was granted, and the team waited for the planet's next transit. Since GJ486b circles its star every 1.467 days, the next opportunity came soon. The telescope locked onto the target again. 1 hour of observation, the same instrument, the same wavelength range, the same analysis methods. If the first signal had been a fluke or an instrument glitch, this new data would have revealed it, but it didn't. The second observation showed the same water vapor signature, the same spectral bump at short wavelengths. The consistency proved the signal was real. Something within that system was indeed producing water vapor. The lingering mystery, was it the planet or the star? Multiple observations also help minimize noise. Every measurement carries uncertainty. Photons arrive randomly. Detectors have flaws. Cosmic rays can strike and create false readings. By averaging data from multiple transits, scientists amplify the true signal while cancelling random errors. It's not a question of distrusting instruments. It's about solid statistical accuracy. The 2 transits occurred months apart, offering another advantage. If star spots were behind the signal, their positions on the rotating star should have changed. Red dwarfs spin roughly every few weeks. If the water signal came from a specific spot that rotated out of view, it would have faded or shifted, but it didn't. That suggests the water might belong to the planet's atmosphere, or that the star is so heavily spotted that the planet always crosses one. Without more data, no one could say for sure. Each transit generates hundreds of gigabytes of raw information, transmitted from the telescope to the Space Telescope Science Institute in Baltimore. There, it passes through calibration pipelines, correcting for instrument quirks, stripping noise, and turning raw photon counts into refined spectra. The cleaned spectra are then analyzed by the science teams using complex computational models. From observation to publication, the process takes months of meticulous work. And this case was particularly groundbreaking. It demanded new methods. No one had ever tried separating planetary atmospheric signals from starspot interference with this level of precision. Researchers developed new starspot simulations, fresh statistical tools, and advanced uncertainty models. In truth, studying GJ486b wasn't just about this single planet. It was about crafting the methods that will help study thousands more like it in the future. The results were both exciting and exasperating. Flat spectra are usually dull, but this one stood out. When the transmission data came back, most wavelengths showed nearly uniform light blockage. A flat spectrum typically means either a planet with no atmosphere or one shrouded in thick, featureless clouds. Scientists had hoped for bold absorption lines, deep valleys marking distinct gases, but they didn't get them. Then, came a subtle rise in the spectrum at shorter wavelengths, between about 1 and 2 microns. The planet seemed to block slightly more light there, right where water vapor absorbs. The rise was small, the uncertainty high, but it was consistent across both observations and matched water vapor's known spectral fingerprint. That tiny bump in an otherwise flat spectrum sparked an international debate. Flat spectra can emerge from different causes. A barren planet produces one because there's no gas to absorb light. An atmosphere thick with clouds can do the same by blocking everything equally. And to complicate things further, starspot contamination can mimic that flatness too. When a planet crosses a starspot, the star's temperature subtly shifts, altering its light in ways that can hide or imitate atmospheric features. Disentangling these effects demands deep modeling of both star and planet. Researchers compared 2 competing models. One assumed the planet had a water-rich atmosphere, simulating how such air would filter starlight under different temperatures, pressures, and cloud conditions. The other assumed an airless planet, but with star spots containing water vapor. They modeled that scenario too, factoring in spot size and heat. Both models fit the data nearly perfectly. Statistically, the difference between them was almost zero. This near tie between 2 competing explanations is something scientists know well. When research pushes the very limits of what instruments can detect, clear answers are rare. Instead, you find traces, hints, overlapping interpretations that all fit within the margin of error. But that's not a flaw in science. It's the very nature of discovery. The first glimpse of anything new is almost always uncertain. Clarity comes later, through sharper instruments, longer observation time, or better analytical techniques. What makes the flat spectrum so intriguing isn't just its lack of features, it's what that emptiness implies about the planet itself. If GJ486b has an atmosphere, it's not behaving as models predicted. Most atmospheric models for hot rocky worlds show clear absorption features, signatures of carbon dioxide, water vapor, or other gases. Seeing almost nothing suggests one of 3 possibilities: a paper-thin atmosphere, an atmosphere made of unexpected materials, or no atmosphere at all. None of these outcomes were what researchers hoped for, but all are scientifically fascinating. The 3 separate analysis methods used to interpret the data tell their own story about how science truly works. Replication is the foundation of credibility. If different teams, using different techniques, all reach the same result, that result becomes far more trustworthy. And that's exactly what happened here. 3 independent research groups took the transmission spectra from both transits and processed them through their own analysis pipelines. The first team used cross-correlation, a mathematical technique that compares the observed spectrum against theoretical molecular templates. The second used Bayesian analysis, a probabilistic approach that weighs the likelihood of various atmospheric compositions. The third employed retrieval modeling, an advanced algorithmic method that runs millions of atmospheric simulations to find the best fit. Despite their differing approaches, all 3 pointed toward the same conclusion: water vapor. Not because anyone expected it or wanted it to appear, but because the data, analyzed rigorously and independently, kept converging on water's distinct spectroscopic fingerprint. The odds of 3 separate methods landing on the same molecule by random chance are astronomically low. That means one of 2 things. Either water vapor truly exists somewhere in the system, or something else is imitating its signals so precisely that even advanced techniques can't tell the difference. The second scenario seems unlikely, but not impossible. Cross-correlation works by generating model templates of different molecules across a range of temperatures and pressures. The computer then shifts, scales, and matches these templates to the observed data. A strong match produces a high correlation score. For GJ486b, water vapor templates scored the highest, while carbon dioxide, methane, and ammonia ranked lower. The method isn't flawless. Noise or instrumental errors can mislead it. But when the signal is genuine, the technique is remarkably reliable. Bayesian analysis approaches the problem differently. Instead of direct template matching, it calculates probabilities. The method begins with assumptions, priors, about possible gases and plausible temperatures, then refines them using the observed data. The outcome is a probability distribution showing which atmospheric compositions are most likely. In GJ486b's case, atmospheres containing water vapor had higher likelihoods than those without. Yet, the error bars remained large. The evidence wasn't definitive, only suggestive. Retrieval modeling is the most computationally demanding of the three. The algorithm runs millions of potential atmospheric setups, varying temperature, pressure, composition, and cloud coverage. Each simulated atmosphere produces a theoretical spectrum. These are then compared against the telescope's real observations, and the models that fit best rise to the top. For GJ486b, those best-fitting models consistently included water vapor. Models without it performed worse. This cross-method agreement is promising, but scientists remain cautious. All three analyses share one major limitation. They cannot determine where the water vapor originates. It could be in the planet's atmosphere, or it could come from the star's surface, hidden within magnetic star spots. Without additional data from other wavelengths, both explanations remain possible. That's why the star spot hypothesis still stands, even after multiple studies pointed toward water. But star spots are far more complex than the dark blemishes most imagine. They are manifestations of magnetic turbulence, chaotic regions where immense magnetic fields erupt from the star's interior and choke the outward flow of heat. The suppressed energy cools these areas, making them darker than their surroundings. Some can grow larger than entire planets. On our own sun, similar phenomena, sunspots, appear and vanish in an 11-year cycle, driven by the sun's magnetic field-flipping polarity. On red dwarfs like GJ486's host star, these magnetic patterns can be even more intense and unpredictable, turning their surfaces into ever-shifting maps of cosmic magnetism. Red dwarf stars like GJ486 follow magnetic cycles similar to our sun's, but far more intense. Their magnetic fields are immensely stronger, and their star spots can cover a massive portion of the stellar surface. Some red dwarfs are blanketed with spots that occupy 10 to 20% of their total area. Imagine if our own sun developed dark patches that large. Earth's climate would swing violently as the sun's brightness dropped by 10% or more. Life on our planet depends on the sun's remarkable stability, but rocky worlds orbiting red dwarfs aren't that lucky. Their parent stars can vary in brightness over just days or weeks, causing drastic shifts in the planet's surface conditions. Inside a star spot, temperatures can plummet to around 4,000 degrees Fahrenheit, or even lower, while the surrounding surface burns at roughly 6,000 degrees. That 2,000-degree contrast creates pockets where molecules that would normally vaporize in intense heat can now exist. Within these cooler regions, compounds like water vapor, carbon monoxide, and titanium oxide become stable, forming molecular fingerprints detectable through spectroscopy. Now here's where things get complicated. When a planet passes in front of such a star, a transit, it might cross directly over these molecular-rich spots. During that crossing, the light we see contains a mixture of signals from both the planet and the star. If the planet has a water-rich atmosphere and the star spot contains water vapor, their signals merge. But if the planet has no atmosphere and merely crosses a water-filled star spot, the data can falsely mimic the presence of an atmosphere. Distinguishing between the two requires observing across many wavelengths of light. Some wavelengths reveal temperature differences between planets and stars. Others reveal pressure differences. Only by combining data across a broad spectral range can scientists tease apart which signal belongs to the planet and which to the star. Unfortunately, the James Webb observations of GJ486b didn't capture enough wavelengths for this separation. The telescope's NIR-spec instrument observed between roughly 1 and 5 microns, ideal for spotting water vapor but too narrow to fully separate planetary and stellar sources. That's why follow-up observations using another instrument, NIRISS, are essential. NIRISS can observe shorter wavelengths, down to about 0.6 microns, where the planetary and stellar models diverge most dramatically. Star spots don't stay still. They rotate with the star. GJ486 completes one full rotation in just a few weeks, so its spots drift across the stellar surface during that time. Between the two Webb transit observations, which were taken months apart, any single star spot would have rotated out of view many times. If the water signature came from one specific spot, its signal should have changed or disappeared between those observations, yet it didn't. The signal remained stable, suggesting two possibilities. Either the water resides in the planet's atmosphere, unaffected by stellar rotation, or the star is so heavily covered in spots that the planet always crosses regions rich in water vapor. Understanding star spots isn't just an academic exercise. It's central to studying planets orbiting red dwarfs. These stars are both creators and destroyers. They provide warmth and light, but their radiation can strip away atmospheres and sterilize entire worlds. Red dwarfs are notorious atmosphere killers. The same ultraviolet and X-ray radiation that nurtures life around our sun becomes a deadly weapon around these smaller, angrier stars. Ultraviolet light carries enough energy to tear molecules apart. X-rays go even further, ionizing atoms and ripping away electrons. When these high-energy photons bombard a nearby planet, chaos follows. Water molecules split into hydrogen and oxygen. Oxygen reacts with nitrogen to form corrosive nitrogen oxides. The hydrogen, being the lightest element, easily escapes into space. Over millions of years, this process can strip away an entire atmosphere. Young red dwarfs are particularly violent. In their first billion years, they unleash massive stellar flares, explosions releasing the energy equivalent of billions of atomic bombs. These eruptions can boost the star's ultraviolet and X-ray output by a factor of 10 to 100 for hours at a time. A planet in close orbit experiences relentless atmospheric assault, a level of radiation far beyond anything Earth has ever faced. Even the sun's most powerful flares pale in comparison. The consequences are devastating. The radiation doesn't just erode atmospheres, it sterilizes surfaces, breaks apart organic molecules, and leaves worlds barren. Scientists estimate that if Earth were placed in GJ486b's orbit, it would lose its atmosphere in less than 100 million years. The stellar wind, a continuous flow of charged particles from the star, acts like a cosmic sandblaster, sweeping away atmospheric gas. Earth's magnetic field protects us from our sun's solar wind by deflecting those charged particles. But around a red dwarf, the stellar wind is far stronger, and planets orbit much closer, amplifying the destruction. Only massive planets with powerful magnetic fields can withstand such punishment. GJ486b, being a rocky planet, may not be so fortunate. Its magnetic strength depends on what's happening deep inside. Magnetic fields arise from molten, electrically conductive cores, like Earth's liquid iron core, which constantly churns and generates our protective field. Mars once had one, but lost it when its core cooled. Venus never developed a strong magnetic field at all. For a planet to maintain such protection, it needs enough internal heat to keep its metallic core liquid and convective. The larger the planet, the longer it can stay molten. GJ486b is about 3 times Earth's mass, which means it might still have an active molten core. Or it could already be geologically dead, its core frozen solid. Scientists don't yet know which is true. Without a magnetic field, the planet is exposed, defenseless against the relentless solar wind. With one, it might resist atmospheric erosion for billions of years, but even then, it would lose some of its air over time. That's why detecting any trace of atmosphere on GJ486b would be extraordinary. The star has had billions of years to strip it bare, yet something, somehow, might still remain. The planet orbits so close to its star that its escape velocity is low, making it easy for gases to drift away into space. By all laws of physics, this world should be completely airless. Yet telescopes have detected traces of water vapor. How could that be possible? The most plausible explanation points to volcanic activity. If GJ486b is still geologically alive, volcanic eruptions could be continuously injecting water vapor into its thin atmosphere faster than the star can strip it away. Just as volcanoes on Earth release steam from deep underground reservoirs, those on GJ486b might be doing the same, but in a relentless cycle. The vaporized gases would be torn apart by radiation, only to be replenished by the next eruption. This fragile atmosphere would exist in a delicate balance, constantly being destroyed and renewed. A brutal equilibrium between creation and annihilation. Picture a planet scarred by thousands of volcanoes, each venting superheated steam into space. The star's intense radiation immediately shatters those water molecules, sending hydrogen streaming off into space. Yet before the atmosphere can vanish entirely, fresh eruptions restore it once more. This endless cycle could be the only way GJ486b maintains. Even a trace of water vapor despite scorching, 800 dF temperatures and relentless stellar bombardment. But what fuels such volcanic activity? Heat. Rocky planets begin life searing hot, formed by violent collisions and gravitational compression that melt their interiors. Over time, radioactive decay from elements like uranium, thorium, and potassium keeps generating energy. A planet 3 times Earth's mass would contain roughly 3 times as much radioactive material, producing 3 times the heat. That heat must escape, and sometimes it bursts through the crust as volcanism. Earth, for example, hosts around 50-70 active volcanoes at any given time. These eruptions release water vapor, carbon dioxide, and other gases, processes that built our atmosphere and oceans over eons. GJ486b might experience a similar process, but with one critical difference. Its atmosphere is constantly being torn away by its star. So to maintain even a paper-thin layer of vapor, its volcanic activity would need to be far more intense, perhaps 10 times greater than Earth's. This may sound extreme, but nature provides a precedent. Io, Jupiter's moon. Io is the most volcanically active world in our solar system, its surface endlessly reshaped by eruptions driven by tidal heating from Jupiter's immense gravity. If GJ486b experiences a similar combination of residual internal heat and radioactive decay, it could theoretically sustain the volcanic output needed to balance atmospheric loss. Unfortunately, we can't yet observe its surface directly. Today's telescopes simply aren't powerful enough. The water itself likely originates from deep within the planet. When worlds form from the gas and dust surrounding young stars, water becomes locked into minerals, frozen in ice, or dissolved in molten rock. As the interior heats up, that trapped water escapes through volcanic eruptions. Earth's mantle, for instance, contains more water than all our oceans combined. GJ486b's interior might hide similar vast reservoirs, feeding eruptions for billions of years. Yet even if volcanism is indeed replenishing the vapor, this wouldn't make GJ486b's atmosphere anything like Earth's. It would be more like a thin, ghostly veil of steam, continually shredded and renewed. Atmospheric pressure might be only a fraction of Earth's, and the air might extend just a few miles above the surface before thinning into space. If you could stand on its blistering terrain, you'd see only a faint shimmer of haze above the glowing rocks. Ultimately, everything depends on one question. Is the detected water vapor truly on the planet? If it is, GJ486b would represent something never before seen. A rocky world wrapped in a pure steam atmosphere, with no nitrogen, no oxygen, no carbon dioxide, just boiling water vapor encasing a planet that should, by all rights, be dry and dead. Earth's atmosphere is composed of about 78% nitrogen and 21% oxygen, with water vapor making up barely 1% on average. Mars's air is dominated by carbon dioxide, and Venus's is thick with carbon dioxide and sulfuric acid clouds. The gas giants, Jupiter, Saturn, Uranus, and Neptune, are mostly hydrogen and helium, with small traces of methane and ammonia. But an atmosphere made of pure water vapor, that's something we've never seen anywhere in our solar system. Kevin Stevenson of Johns Hopkins University put it best: there is no comparable atmosphere in our own solar system. That statement carries enormous weight. It means scientists have no reference point, no known world to compare it to. They can't simply say, it should behave like that planet. Instead, they must build new atmospheric models from scratch, combining physics and chemistry in ways never before tested. On GJ486b, everything changes. The temperature dictates how water molecules behave. The pressure determines how thick the atmosphere can be, and the stellar radiation decides how long it can last. Water vapor reacts differently depending on these factors. On Earth, water exists in all 3 familiar phases: ice, liquid, and vapor, and shifts between them at specific temperatures and pressures. But GJ486b's surface is far too hot for ice or liquid water. There, everything would exist as vapor. This vapor wouldn't just float harmlessly, it would react chemically with the rocky surface. On Earth, similar reactions happen in volcanic vents and hot springs, but on GJ486b, such reactions might occur across the entire day side of the planet. Superheated water vapor could slowly corrode minerals, breaking down rocks molecule by molecule. Meanwhile, the star's intense ultraviolet radiation would bombard the upper atmosphere, splitting water molecules into hydrogen and oxygen. The lightweight hydrogen would quickly escape into space, while the heavier oxygen might either escape more slowly or react with surface metals, oxidizing them, turning the planet's crust into rust-like compounds. This constant imbalance, with hydrogen escaping faster than oxygen, means volcanic eruptions would need to continuously inject fresh water vapor to maintain the atmosphere's composition. If enough vapor exists, GJ486b's atmosphere could generate violent weather patterns. The scorching day side heated to around 800 degrees, would drive columns of rising steam, while the cooler night side would see descending flows of condensing vapor. Between the two, winds could howl at supersonic speeds, perhaps over 1,000 mph, moving heat from day to night and preventing extreme temperature differences. These ferocious winds would likely create turbulent storms and weather systems unlike anything ever seen on Earth. But how thick is this atmosphere really? No one knows. It could be dense and crushing, like Venus's, or whisper-thin, barely enough to detect. The current transmission spectroscopy used by the James Webb Space Telescope can only identify the presence of water vapor, not how much of it there is. Future missions may uncover more by studying how the planet's atmosphere redistributes heat across its surface. Still, before scientists can analyze its weather, chemistry, or structure, they must first confirm that this atmosphere truly exists. And that's no easy task, because stars are blindingly bright. A typical star outshines its planets by billions of times. Trying to observe a planet next to its star is like trying to spot a firefly beside a floodlight. The glare drowns out everything else. For decades, this limitation forced astronomers to detect planets only indirectly, by studying how they tug on their stars or dim their light during transits. Then came a breakthrough: the invention of the coronagraph. These ingenious devices block a star's overwhelming light while allowing the faint glow of nearby planets to pass through. The concept sounds simple, but the engineering is anything but. Coronagraphs use precisely shaped masks and carefully angled mirrors to cancel starlight with astonishing accuracy. The James Webb Space Telescope carries several advanced coronagraph designs, each fine-tuned for different observing conditions. For transiting planets like JWST, Webb doesn't use a coronagraph, because the planet passes directly in front of the star, letting scientists study the starlight filtered through its atmosphere. But for other, more distant exoplanets, coronagraphs are essential. They're the only way to pierce the glare and glimpse the faint worlds orbiting those distant suns. The masks themselves are true feats of engineering, masterpieces of precision and design. Each one is crafted into intricate patterns of concentric circles or spirals, created using advanced mathematical principles that control how light diffracts and interferes. When starlight strikes the mask, its unique pattern forces different light waves to cancel each other out through destructive interference, reducing the star's brightness by factors of thousands or even millions. Meanwhile, the faint light from a planet slightly offset from the star isn't affected in the same way. It slips through with minimal loss, revealing what would otherwise remain invisible. But there's a catch. Coronagraphs only function flawlessly if the telescope's optics are near perfect. Even the tiniest flaw, a microscopic imperfection in a mirror, a minor vibration, or a bit of thermal expansion, can create false signals that mimic real planets. That's why engineers spend years meticulously testing and calibrating coronagraphs. They first observe stars known not to have planets, producing reference images that show what pure artifacts look like. Then, they study stars with confirmed planets to confirm the system's accuracy. Only after countless validation tests can astronomers fully trust the data. The James Webb Space Telescope's coronagraphs operate in the infrared spectrum, light invisible to human eyes but ideal for studying cooler celestial objects like planets. Rocky worlds emit most of their light in infrared wavelengths due to their surface temperatures, while gas giants glow from residual heat left over from their formation. Observing in infrared dramatically improves the contrast between planet and star, reducing the brightness gap from billions to just millions or thousands, making all the difference. In the case of JWST, the telescope didn't need to use a coronagraph because the planet transits directly across its star. During a transit, the planet blocks a tiny portion of starlight, and the telescope measures that brief dip in brightness. By analyzing the spectrum of light that filters through the planet's possible atmosphere during this event, scientists can determine its composition. No coronagraph was required for this setup. But such instruments remain essential for directly imaging planets that don't transit, especially in future attempts to photograph Earth-like worlds orbiting Sun-like stars. The next challenge lies in selecting the right instrument for the task. The James Webb Space Telescope carries two instruments capable of studying planetary atmospheres, each with distinct methods and complementary insights. NIRSpec, near-infrared spectrograph, observed JWST and detected signals of water vapor. Meanwhile, NIRIS, near-infrared imager and slitless spectrograph, could help determine whether that water originates from the planet itself or from its host star. To understand how, it's important to know how these instruments work. NIRSpec covers wavelengths between 0.6 and 5.3 microns, a key range for detecting molecular absorption patterns. Water vapor absorbs strongly around 1.4 and 2.7 microns, carbon dioxide around 4.3 microns, and methane around 2.3 and 3.3 microns. NIRSpec spreads these wavelengths into high-resolution spectra, revealing which molecules are present and in what concentrations. However, NIRSpec has one weakness. Its sensitivity decreases between 0.6 and 1.0 microns, exactly where the difference between planetary atmospheres and stellar star spots becomes clear. Below 1 micron, computer models show distinct spectral fingerprints. Hot planetary atmospheres produce one pattern, while cool star spots generate another. Because NIRSpec struggles to see this range clearly, it can't definitively tell the two apart. That's where NIRIS comes in. It operates across 0.6 to 2.8 microns, with exceptional sensitivity below 1 micron. Perfect for solving this mystery. Even more importantly, it uses single object slitless spectroscopy, SOSS, a powerful technique designed for bright stars like red dwarfs. NIRIS can capture an entire transit in real time, creating time-resolved spectra that reveal how the signal changes as the planet moves across the star's face. If the water vapor comes from the planet's atmosphere, the spectral signal will stay constant throughout the transit. The planet carries its atmosphere along, so nothing changes. But if the signal originates from star spots, the strength and shape of that signal will vary as the planet crosses regions of differing temperature and size. In essence, these instruments work hand in hand, each uncovering a different layer of the mystery, bringing us one step closer to understanding not just GJ486b, but the complex dance of light and shadow that defines our view of alien worlds. The distribution of star spots across the stellar surface isn't uniform. Some regions are densely packed with spots, while others are nearly spotless. As the planet moves across the star's disk during transit, it passes over these different regions, potentially creating a time-varying water vapor signal. This means the water vapor signature could fluctuate depending on which part of the star's surface the planet is crossing. NIRIS can capture this variation by observing the spectrum at shorter wavelengths, where the difference between the two scenarios, planetary or stellar water vapor, becomes clear. According to theoretical models, water vapor in a planet's atmosphere produces a spectrum that rises towards shorter wavelengths, while water vapor in star spots shows a falling spectrum. The reason lies in temperature. A planetary atmosphere heated to about 800 degrees behaves very differently from a stellar photosphere that reaches 6,000 degrees, with embedded spots of around 4,000 degrees C. NIRIS's sensitivity in this wavelength range should be able to detect this divergence, providing a definitive answer about whether the water comes from the planet or the star. However, there's one problem. The NIRIS observations haven't been completed yet. The research team has proposed them, but telescope time on the James Webb Space Telescope is fiercely competitive. Hundreds of proposals fight for a limited number of observing hours. Some are approved right away, others wait for years. The GJ486b NIRIS observations were accepted, but their exact schedule remains uncertain. Until that data is collected and analyzed, the mystery remains unresolved. Then, in August 2024, a new study dropped, and it shook the entire debate. The paper, boldly titled "No Thick Atmosphere on the Terrestrial Exoplanet GJ486b," presented results from 2 additional telescope observations using a completely different method known as secondary eclipse spectroscopy. Unlike transit observations, where astronomers watch the planet pass in front of the star, secondary eclipse spectroscopy examines what happens when the planet passes behind it. During this moment, the total brightness of the system drops slightly because the planet's thermal emission disappears from view. By measuring how much the brightness decreases at various wavelengths, scientists can determine the planet's dayside temperature and look for emission features that indicate an atmosphere. If GJ486b had a thick atmosphere, it would redistribute heat between its day and night sides and show clear molecular signatures in the infrared spectrum. But the new data showed neither. The planet's dayside temperature was measured at 865 degrees plus 14 deg. Remarkably precise, but far more revealing is what that temperature implies. Scientists compared this temperature to what's expected for a bare, airless rock with no heat redistribution. An airless body absorbs starlight on its day side and re-emits it directly as infrared heat. When researchers calculated the theoretical maximum temperature for such a planet, GJ486b's actual temperature turned out to be 97% of that maximum, nearly identical. That result tells a clear story. The planet doesn't redistribute heat effectively, meaning it likely lacks a thick atmosphere. If it did, the heat from the star-facing side would circulate to the night side, cooling the day side noticeably below the maximum. But it doesn't, suggesting GJ486b is probably a bare, rocky world. The study concluded that the planet either has no atmosphere at all, or an extremely thin one, containing less than 1% water vapor, or fewer than 1 part per million of carbon dioxide. This directly contradicts earlier transmission spectroscopy results that hinted at the presence of water vapor. So how can both be true? The key lies in how the two methods sample the planet. Transmission spectroscopy analyzes starlight that passes through the uppermost layers of a planet's atmosphere during transit, the thin, high-altitude regions. Secondary eclipse spectroscopy, on the other hand, measures thermal emission from the entire day side, probing much deeper layers. It's possible that GJ486b has a very thin, high-altitude layer of water vapor, just enough for transmission spectroscopy to detect, but too little atmosphere to affect temperature or heat transport. Alternatively, the earlier detection might have been an illusion, caused by stellar water vapor in star spots, not from the planet at all. The secondary eclipse results strongly support this latter explanation, because they show no signs of atmospheric heat redistribution. If GJ486b truly had a thick, water-rich atmosphere, it would carry heat across its surface, yet the data says otherwise. The most likely conclusion: the water vapor doesn't belong to the planet. The August 2024 paper perfectly illustrates the scientific process in action. One team makes a claim, another tests it with a different approach. The results clash, sparking new investigation. Now, astronomers must determine whether one finding is wrong, or if both are correct, but describe different layers or phenomena. The debate continues, but the latest evidence tilts the scales toward the star spot interpretation. Still, no thick atmosphere doesn't mean a complete vacuum. Even Mercury, the most barren planet in our solar system, has a faint exosphere, a whisper-thin layer of atoms knocked off its surface by solar wind. The Moon has a similar trace atmosphere. These exospheres have pressures millions of times lower than Earth's, far too thin to breathe, hear, or feel, but detectable with sensitive instruments. So when scientists say GJ486b might be airless, they mean something like this: an atmosphere so sparse it's practically non-existent. For context, Earth's surface pressure is about 14.7 pounds per square inch, caused by the weight of the air above. Climb a mountain and pressure drops because there's less air overhead. Leave the atmosphere entirely, around 60 miles up, and pressure near zero. By comparison, Venus has surface pressure 90 times greater than Earth's, like standing 3,000 feet underwater. The air would crush you long before the heat did. Mars, on the other hand, has a surface pressure of just 0.6% of Earth's, barely enough to count as an atmosphere. GJ486b likely falls closer to Mercury's realm, a world with a trace of gas, but for all practical purposes, a naked, airless rock orbiting its fiery star. Mars's atmosphere is thin, far too thin for humans to breathe, yet still thick enough to shape the planet's weather, drive dust storms, and form clouds. These are what scientists call thick atmospheres. In the planetary sense, they actively influence the planet's climate and surface. But GJ486b might have something far weaker. Imagine an atmosphere just 1/10, 100th, or even 1,000th the pressure of Mars's. At such levels, calling it an atmosphere almost becomes misleading. It would be more accurate to describe it as a faint haze of stray molecules, bouncing off the planet's surface before quickly escaping into space. An atmosphere that thin couldn't move heat around, create weather, or shield the surface from radiation. It would barely interact with incoming starlight. Yet, if a few molecules were concentrated high enough above the surface, they might still leave a detectable trace in transmission spectroscopy, the technique that first hinted at water vapor. That's why the August 2024 study chose its wording carefully. The phrase "no thick atmosphere" doesn't mean no atmosphere at all. It specifically rules out Earth-like or Venus-like air pressure, while leaving room for something ultra-thin, perhaps less than 1% water vapor. That less than 1% is a critical detail. Earth's atmosphere averages about 0.4% water vapor, so even under this definition, GJ486b could still host a trace of water, just not enough to affect heat transport or create measurable weather patterns. This subtle distinction matters because how we define an atmosphere could decide whether GJ486b represents a historic breakthrough or a false alarm. If it truly possesses even a wisp of gas, thinner than Mars's but undeniably real, it would become the first rocky exoplanet confirmed to have an atmosphere. That would mark a major milestone in understanding how planets form and evolve. But if the water vapor actually comes from star spots rather than the planet, then GJ486b is just another bare rock, and the search for the first rocky exoplanet atmosphere continues. This isn't just a semantic debate. It touches a deeper scientific problem, the M-dwarf planet dilemma. Red dwarf stars, which make up about 70% of all stars in the Milky Way, are surrounded by countless rocky worlds. Yet many may be atmospheric graveyards, planets that once had air but lost it long ago. In their youth, red dwarfs are violent. During their first billion years, they unleash intense radiation storms, with ultraviolet light and X-rays flaring to many times their normal brightness. These outbursts strip away planetary atmospheres layer by layer, blasting them into space until only bare rock remains. This creates a grim picture. Billions of rocky planets orbiting red dwarfs, but most of them lifeless and airless. Scientists have debated for decades whether any of these worlds could survive such punishment. Some argue that no rocky planet orbiting a red dwarf can hold on to an atmosphere. The radiation is simply too strong and the planets orbit too close. But others believe there are survival mechanisms. Powerful magnetic fields that deflect stellar wind, massive gravity that locks in gases, or volcanic outgassing that replenishes lost air faster than it escapes. Until recently, this was all theoretical. There was no way to tell which side was right. Then came GJ486b, a rocky world about 3 times the mass of Earth, orbiting an older, quieter red dwarf. It seemed like the perfect test case. Massive enough to hold air, and orbiting a star long past its violent youth. When the James Webb Space Telescope detected signs of water vapor, it sparked hope. Maybe atmospheres could survive around red dwarfs after all. Maybe billions of these worlds could still be habitable. But the August 2024 paper, showing no thick atmosphere, reignited skepticism. Maybe red dwarfs really are graveyards. Maybe most of their planets lost their air eons ago. This question has profound implications for the search for life. Most biosignatures, like oxygen and methane, require an atmosphere to be detectable. If rocky planets around red dwarfs can't retain their air, then searching for life there may be futile. Scientists would need to focus on planets orbiting sun-like stars, which are rarer. That would drastically reduce the number of promising targets and push the timeline for discovering extraterrestrial life from decades to centuries. There's also the matter of planetary mass. Larger rocky planets have stronger gravity, helping them retain atmospheres more effectively. GJ486b, with its 3 Earth mass, sits near the upper limit for rocky planets. If even it struggles to hold an atmosphere, then smaller Earth-sized planets likely have no chance. On the other hand, if GJ486b does turn out to have even a thin veil of gas despite its harsh conditions, it would prove that atmospheres can endure under the right circumstances, offering new hope for smaller, more Earth-like worlds. For now, the issue remains unresolved. One set of observations points to water vapor, another points to bare rock. Until further data confirms or refutes the existence of atmospheric gas on GJ486b or similar planets, the M-dwarf atmosphere mystery remains open. But to unravel it, scientists are now turning to another planet, one that might finally reveal the truth. Venus and GJ486b are like distant cosmic twins. Both are rocky worlds with scorching surface, temperatures near 800 degrees, and orbit much closer to their stars than Earth does. Yet, despite these similarities, they couldn't be more different. Venus is wrapped in a suffocating atmosphere of carbon dioxide, while GJ486b may have none at all. Understanding why these two seemingly similar planets evolve so differently could unlock key insights into how worlds form and transform over time. Venus's atmosphere is massive, about 90 times heavier than Earth's. The surface pressure there is equivalent to standing nearly 3,000 feet underwater. Composed of 96% carbon dioxide and covered by clouds of sulfuric acid floating about 30 miles above the surface, Venus reflects most sunlight back into space, giving it a bright albedo. Still, enough sunlight seeps through to heat the surface, while the thick CO2 blanket traps that heat through a runaway greenhouse effect, keeping the planet searing hot both day and night. But Venus wasn't always hellish. It likely began with oceans of liquid water, much like early Earth. However, orbiting much closer to the Sun, Venus received nearly twice as much solar energy. This extra heat caused more ocean water to evaporate into the air as water vapor, a potent greenhouse gas. As the atmosphere thickened, it trapped even more heat, evaporating the remaining oceans in a self-reinforcing loop. Eventually, ultraviolet radiation split the water molecules apart. Hydrogen escaped into space, while oxygen reacted with surface rocks. The planet's water was gone, replaced by volcanic carbon dioxide that built up into the suffocating atmosphere we see today. JJ486b may have experienced a similar fate. It too might have started with vast oceans, but its close orbit around a red dwarf star subjected it to intense stellar radiation. That heat likely evaporated its oceans early on, filling the atmosphere with water vapor. The star's ultraviolet light would then have torn those water molecules apart, even faster than the Sun did on Venus. Hydrogen escaped into space, while oxygen either escaped or bonded with surface materials, stripping the planet of water within a few 100 million years. Unlike Venus, though, JJ486b may not have produced enough volcanic carbon dioxide to rebuild its atmosphere. And even if it did, the powerful stellar wind from its host star likely stripped that gas away as fast as it formed. The result a barren, airless world. Here's where their difference becomes fascinating. Venus retains its thick atmosphere, partly because it's far enough from the Sun that the solar wind can't easily blow it away. Even without a strong magnetic field, its dense atmosphere acts as a shield, absorbing harmful ultraviolet and charged particles. JJ486b, on the other hand, orbits much closer to its star, where stellar winds are far stronger. Even if it tried to form an atmosphere through volcanic outgassing, those same winds would likely strip it faster than it could rebuild. Temperature also plays a vital role. Venus is hot because of its thick greenhouse atmosphere. Without it, the planet would be much cooler. JJ486b, however, is hot because it lies so close to its star. Even if its thin atmosphere vanished entirely, its surface temperature would barely change. This contrast reveals a powerful truth. Venus traps its heat from within. JJ486b simply endures it from without. This comparison between Venus and JJ486b reveals just how fragile the balance of planetary evolution can be. Small differences in a world's distance from its star, stellar type, or internal properties can completely alter its fate. Venus ended up smothered by too much atmosphere. JJ486b, by contrast, may have lost almost all of it. Both are infernos, but each in its own way. These contrasts raise a crucial question. Would detecting even the faintest atmosphere on JJ486b count as a first in human history? Scientists have already discovered hundreds of exoplanet atmospheres, but all of them belong to gas giants. Massive worlds like Jupiter and hot Jupiters, orbiting close to their stars, reveal clear spectral fingerprints of water vapor, methane, carbon monoxide, and even vaporized metals. The techniques used to study them, transmission spectroscopy and secondary eclipse observations, work brilliantly on large, thick atmospheres. But rocky planets are a different story. They're smaller. Their atmospheres, if they exist at all, are far thinner, and their signals are buried deep in noise. Until JJ486b, no one had ever confirmed atmospheric gas around a rocky exoplanet. If proven real, this discovery would shatter a decades-old barrier. Since the first confirmed exoplanet in 1995, thousands of planets have been found, hundreds of gas giants studied in detail, but not one rocky planet has shown definite signs of air. No Earth-like or Venus-like atmosphere has ever been confirmed. That's because the challenge is immense. Small planets produce faint, delicate spectral signatures that are easily drowned out by stellar activity or instrumental limitations. Finding a true rocky exoplanet atmosphere would be revolutionary. It would prove these techniques actually work for small worlds. validating decades of technological progress. It would justify the massive investment in next-generation telescopes designed to study Earth-like atmospheres. Funding would pour into missions searching for habitable planets, accelerating the hunt for life beyond Earth. But the opposite outcome matters too. If GJ486b turns out to be airless, it would imply that rocky planet atmospheres are even more elusive than scientists feared. Current instruments might simply lack the sensitivity to detect such faint gases. It would mean the next breakthroughs could take not just years, but decades, perhaps a challenge left to the next generation of astronomers. Right now, the answer hinges entirely on ambiguous data. If transmission spectroscopy truly detected water vapor belonging to the planet, then GJ486b would become the first rocky exoplanet with a confirmed atmosphere, a historic first. But if that water vapor came instead from the star itself, from star spots mimicking the signal, then it's another false alarm, and the search continues. As planetary scientist Sarah Moran put it perfectly, we see a signal, and it's almost certainly due to water. But we can't yet tell if that water belongs to the planet's atmosphere. That honesty is essential. Premature claims that later collapse under scrutiny only damage scientific credibility. So, for now, scientists wait, gathering more data, refining their methods, and studying other rocky worlds around red dwarfs to compare results. Eventually, the question will be answered. Either GJ486b has an atmosphere, or it doesn't. Either it's the first of its kind, or the search goes on. But no matter which way it turns out, the implications reach far beyond this single world, 26 light-years away. If GJ486b can cling to even a wisp of air despite 800 degrees of heat, relentless radiation and tidal locking, then it means something extraordinary. Rocky planets can endure in brutal environments. Now imagine another world like GJ486b, but orbiting just a little farther from its star. Cooler, calmer, less battered by radiation. On such a planet, water vapor could persist longer. An atmosphere could stabilize. Clouds could form. Rain could fall. Oceans might even exist. If GJ486b, the extreme case, manages to hold onto an atmosphere, then more temperate red dwarf planets almost certainly can too. And that means the universe may still be full of worlds with skies, weather, and maybe even life. The billions of rocky planets orbiting within red dwarf habitable zones across our galaxy remain promising targets in the search for life. But if GJ486b truly lacks an atmosphere, that changes everything. If a planet this large, with its strong gravity, can't retain atmospheric gases, what hope is there for smaller, Earth-sized worlds? The answer might be grim, perhaps none. It's possible that rocky planets orbiting red dwarfs universally lose their atmospheres during their star's violent early years, leaving behind billions of sterile, airless rocks. If that's true, the search for life must shift toward planets orbiting sun-like stars. Rarer, dimmer, and much harder to study. Still, there's a middle ground. Maybe only massive rocky planets, like GJ486b, several times Earth's size, can hang on to an atmosphere around red dwarfs. That would mean millions of super-Earths could still remain viable homes for life. The galaxy wouldn't be teeming with inhabited worlds, but it wouldn't be lifeless either. Life would simply be harder to find, but not impossible. This discovery could even force scientists to rethink what the habitable zone really means. Traditionally, it's defined by distance from a star, where temperatures allow liquid water to exist. But if planets close to red dwarfs can't keep their atmospheres, then temperature alone doesn't determine habitability. Atmospheric survival becomes the key. A planet might be cool enough for liquid water, yet remain uninhabitable without air. That means the true habitable zone could be much narrower than we imagined. Another consequence involves life's resilience. Suppose GJ486b has a thin, constantly shifting atmosphere, stripped away and replenished again and again. That unstable balance might prevent life from forming at all. Life needs long-term stability, consistent conditions that last for millions of years. On Earth, even the toughest extremophiles thrive in environments that remain stable, no matter how harsh. Still, perhaps alien extremophiles could adapt to these transient worlds. Each rocky planet we study brings us closer to understanding which types can hold onto air and which can't. Every new detection, every atmospheric measurement adds another piece to the puzzle. Eventually, clear patterns will emerge, helping scientists target the right worlds for future life-hunting missions. But one misconception must be cleared up. finding water vapor does not mean finding life. Water is essential for life as we know it, but water itself isn't alive. Many lifeless worlds contain water: Jupiter, Saturn, comets, even our own moon. Water alone tells us nothing about biology. True biosignatures are unique combinations of gases that can't easily exist without life, like oxygen and methane together. On Earth, oxygen persists only because living organisms continually replenish it. Without life, geological processes would strip it away within a few million years. However, even oxygen alone isn't conclusive. Non-biological reactions can also create it. The strongest evidence for life comes from multiple gases existing together in unstable combinations, like oxygen with methane, or methane with nitrous oxide. These chemical pairings shouldn't coexist unless something, likely life, is constantly regenerating them. Even then, scientists can only talk about confidence levels, 10%, 90%, but never 100% until we directly observe living organisms. That's why GJ486b's possible water vapor detection, even if confirmed, tells us nothing about life. Its surface is a scorching 800 degrees, utterly inhospitable. The water vapor likely comes from volcanic activity, not biology. It's scientifically fascinating, but biologically irrelevant. Unfortunately, media headlines often distort such discoveries, claiming water found on alien world, as if that means alien life is imminent. In truth, scientists might simply be detecting volcanic steam, or even contamination from the host star. Managing expectations is vital to avoid public disappointment, and to preserve trust in science. False positives have happened before, apparent biosignatures, that turned out to be instrument errors or data misinterpretations. Each false alarm damages credibility, creating a boy who cried wolf effect. That's why researchers must remain cautious and transparent about what's truly been found. In the end, GJ486b is a stepping stone. Whether or not it has an atmosphere, it serves as a training ground for the techniques scientists will use on more Earth-like planets in the future. The James Webb Space Telescope and its successors will refine these methods, learning how to separate planetary signals from stellar interference and identify the best wavelengths for study. When we finally detect a truly habitable world, the lessons learned from GJ486b will have paved the way. That brings us to the final question: what happens next? The story of GJ486b is far from over. Upcoming observations with the James Webb Space Telescope's NIRISS instrument could finally reveal whether the detected water vapor comes from the planet itself or its parent star. These crucial observations are already scheduled, awaiting execution. Within the next year or two, scientists will analyze the data and publish their findings, results that could reshape our understanding of planetary atmospheres forever. If the data shows that the water vapor originates from the star, the mystery ends there. GJ486b would likely be an airless world, and the search for the first rocky exoplanet with an atmosphere would continue elsewhere. But if the vapor proves to be planetary, even a thin, fragile atmosphere would be a monumental discovery. The first real glimpse into the atmosphere of a rocky world beyond our solar system. Beyond GJ486b, dozens of similar worlds await. Astronomers have already catalogued hundreds of rocky exoplanets orbiting nearby red dwarfs, many ideal for atmospheric study. Some are even more promising than GJ486b. Their stars less violent, their alignments more favorable, their conditions just right for observation. Yet telescope time is precious. Every hour spent on one planet means another goes unobserved. Careful choices must be made. The Nancy Grace Roman Space Telescope, set to launch around 2026-2027, will soon join the hunt. With its advanced instruments, Roman will be able to directly image some exoplanets instead of relying solely on transits. Together, Webb and Roman will form a powerful partnership, complementing each other's strengths, sharing discoveries, and perhaps finally, identifying the first confirmed atmosphere on a rocky world. Meanwhile, on Earth, the next generation of ground-based observatories is rising. In Chile, the extremely large telescope is under construction, its massive 39-meter mirror poised to collect more light than any telescope in history. Despite the challenge of Earth's own atmosphere, advanced adaptive optics will allow it to peer deep into alien skies. studying worlds orbiting nearby stars with unprecedented detail. Looking ahead, even more ambitious missions are on the drawing board. Telescopes purpose-built to study Earth-like planets, equipped with instruments fine-tuned to detect biosignatures. These missions could take decades to build and billions to fund. Whether they move forward depends heavily on what the James Webb Space Telescope finds now. If Webb confirms multiple rocky exoplanets with atmospheres, the momentum and funding for future life-finding missions will accelerate. If not, the focus of exploration may shift. Either way, every discovery, every null result, moves science closer to its ultimate goal, finding life beyond Earth. GJ486b may not host life, it might not even have an atmosphere, but it serves a higher purpose. Each study, each observation, sharpens our tools and deepens our understanding. Science advances through patience, precision, and persistence, exactly the qualities this investigation demands. In just a few years, we'll know the truth. We'll know if rocky planets around red dwarfs can hold onto their atmospheres, and where in the galaxy to search for truly habitable worlds. These answers will redefine how we see our place in the universe, determining whether the Milky Way teems with living worlds, or whether we are alone amid endless silence. 26 light-years away, a small rocky planet circles its dim red sun, either shrouded in vapor or bare as stone. Back on Earth, scientists watch, calculate, and wait. The data is coming. The mystery endures, because out there, in the faint glow of another star, the truth is waiting, written in light, drifting across the cosmic dark.